here is a complicated example. Basically, we got here is a rational function, and I've given you the derivatives. Okay, you should be able to, you should check these to make sure that they make sense. So x cubed over 9 minus x squared. This is going to have an oblique asymptote because the numerator is 1 degree higher than the denominator. Okay, here's the derivative. The derivative equals 0 at x equal to 0, and this is a difference of squares here, so we'll be able to factor that. And here's the second derivative, and it will equal 0 at 0, x equal to 0, and because this is a sum of squares, that's it. Now, the derivative is undefined at x equal to 3. So is the function. And the second derivative. So at x equal to 3 and negative 3, sorry, because this is a difference of squares. So we're going to have two vertical asymptotes, x equal to 3 and x equal to negative 3. Okay, so let's take a look at the increasing decreasing table. So f primed equal to 0. So there's factoring the top. So root 27 minus x, root 27 plus x. It's a difference of squares. Root 27 is 3 root 3. Okay, here's what we get on the bottom, so we can see the vertical asymptotes. So we've got some critical numbers here to put into the increasing decreasing table, and it's going to be plus or minus root 27, 0, 3, and negative 3. So that's a lot of information to put in here. Okay, I'm circling the ones where the function exists, and I'm not circling the ones where the function doesn't exist. So these will be the asymptotes. That just tells me that that's where the function, it does exist. Okay. So we look at all the factors to this derivative here, and we put them in this table. There's a lot of information. When you get to the point where you're looking at the signs, you look at where does x squared change signs. It changes signs here. Okay, so it's positive on the left, positive on the right. It's not actually going to change signs because x squared is always positive. 3 root 3 minus x, well, this is a negative slope. So it's going to be positive on the left side of 3 root 3 and negative on the right. This is 3 root 3 plus x. So it's a positive slope. It's going to be negative on the left of that 0 and positive on the right. This is always positive because it's squared. This is always positive because it's squared. Okay, so now we can look down at the bottom of the table and determine the local max and local min from these increasing, decreasing pieces. Okay, so the derivative is negative, positive, 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 negative, because of looking at these signs and multiplying them. We've got decreasing to increasing, so we have a local min at this value here. Then it's increasing all the way to 3 root 3, and we have a local max at that point because it's up and then down. So we can calculate those. We have nothing here at 0, even though the function exists there, but it doesn't change from increasing to decreasing, so we don't have a local max or min there, it looks like. So we can calculate those by subbing them into the original function, and we get these values. Okay, you can check that. Now the concavity chart. So the concavity chart is, well, it's this piece here. We got some critical numbers, the vertical asymptotes, and where it equals 0, the second derivative. Okay, so we plug those in and do the same process. This is what we get for the concavity chart. Okay, then we've got these values here. I'm just going to let you check this. The oblique asymptote, here's the long division, and you've got this part. Okay, so the interesting part here is looking at the end behavior, looking at the limits as x goes to infinity. Well, we've got to find the oblique asymptote, so we've got to do the long division. X cubed divided by 9 minus x squared. When you divide that out, you get negative x, and you get a remainder of 9x. Okay, So if you looked at x cubed divided by 9 minus x squared, which is the function, then using this division we get f of x equal to negative x, which is this result, plus 9x, which is the remainder, divided by this piece here. So you can check to see that's true. If you've got a common denominator here and figured this all out, you get the original function, which was x cubed over 9 minus x squared. As x goes to infinity here, this piece goes to 0. So the whole reason we get an oblique asymptote here is because this remainder piece just disappears as x goes to infinity, and we just get the result on top, which is the line. So the oblique asymptote is a diagonal line. Okay, so y equal to negative x is the oblique asymptote in this case. Now we take all this information and we make the graph from it, and this is what we get. Okay, so you have to take all the oblique asymptote is here, you graph that in, you graph in the dotted lines for the vertical asymptote. Then you graph in the local min, the local max, the inflection point. You look at the concavity around those and around the inflection points and in the intervals of concavity, and you plot that in and make sure it's increasing and decreasing in the right places based on your increasing and decreasing chart. Okay, and this is the graph that you would get.